I butchered that.
Yeah,
My apologies.
that's nice.
Talking about Pythran, another Python compiler.
So hi everybody. So I have only 20 minutes, question included, so I'll try to go as fast as my English make it possible. So this is mostly a personal project, but I received some funding, so first I have to thank them. So SILKAN is a French and American company that gave me a grant. Part of my postdoctoral position is granted by the CARP project, so the small fish there. I received a grant to come here to talk with you, so thanks so much to the SciPy organizers. And I am an associate researcher at Télécom Bretagne, and a few students, excellent students, are working on the project, so I have to thank them too. So, to begin with, I'd like to point out that I will not only talk about Python, but also about C++, compilation, parallelism. So, this is not exactly the skills you may have in the audience, but any of them is okay to follow. So, basically, scientists have a lot of tools available when they want to do scientific computing, and Python is one of them, so I will not speak about the others. As part of my job, I am an HPC engineer, and I tend to see people moving from the other language to Python, so that's great news. And even when you are doing scientific computing in Python, you have plenty of tools, so basically you're using SciPy, but then when you want optimized kernel, there are plenty of possibilities. I'm listing some of them here. There is the PyPy project with the NumPy ongoing project, Numba. You can do hardcore programming using F2P or Swig or Siphon. Any of them is right, and I'm going to present another project. We can discuss why it is relevant or not. This is a regular IPython session. You just import NumPy, run a function. What? Oh. And time it, so it's okay, it works. And if I'm using Pythran, so I load the Pythran magic, and then specify the very same function with just a few annotations as a comment. There is a motivation behind the comment. I will explain it later. And then you just run the same function. This is NumPy, so this is optimized C behind, but still, whoops, we get a factor of more than 10. Okay, so we did not change anything in the code. We just translated it to C++, performed several optimization, and it runs much faster. So the rest of the talk will be why, on how are we doing this. So this is a big picture behind the compiler. So Pythran is a compiler that takes a whole Python module with a few restrictions. So it's an embedded language into Python. You can add OpenMP annotation to your Python module to make it run in parallel. Pythran will generate a meta program in C++, and it will then instantiate this meta program for the particular type you are giving to him, plus link to several existing libraries, and you get your native module through G++ or Clang. So the goal of Pythran is, first, we need performance. So we are okay to sacrifice a few language features to get the performance. And the poor feature we sacrifice is mainly eval or this kind of thing, and user classes, which is not that a big deal when you do scientific computing. So it's embedded in Python, so backward compatibility is kept, it matters. You don't modify your Python code to run it through Pythran, and it's modular compilation. You put all your kernels in a module, you accelerate this module, and the remaining remains in Python. So you don't turn your whole code into native code, but only the part that matters, the part where you spend a lot of time. So to do this, we don't only translate. That's a thing other compilers are doing. We do static compilation and static optimization. We do vectorization and parallelisation. So that's a bit much more than the others are doing. So it motivates the existence of the project. One very funny thing is, if you look at C++ 11, you can express the same kind of thing as you do in Python. Okay, it's a bit more verbose, but you have very similar things. The dot product function in Python and the dot product function in C++, from the user point of view, you call them the same. It's just a bit more boilerplate to have it run in C++, but in the end, you have really faster code. So if a tool can translate the one above to the one below for you, then it's good. And that's why that's what Pythran is doing. So Pythran is generating the kind of code at the bottom. So this is a meta program, and then it's instantiated for the types you give him. So using C++ as a backend is a nice idea because we benefit from the standard template library. We have all this object-oriented programming, meta programming that French people tend to like. We have some kind of type inference in the new standard. We have variadic templates which make it possible to emulate a lot of Python syntax. And still, so we have this high-level stuff and the low-level stuff we need to get real performance. When I hear Julia is almost as fast as C, but is it as fast as optimized C with vector instruction and parallel annotation? Of that I am not sure. So we can benefit from this when we are doing hardcore C++ programming. So static compilation requires static type inference, but Pythran only requires type annotation for your exported functions. So if you have intermediate function, you don't need to annotate them. You don't need to annotate the variable declaration or your internal list, only the interface. And we infer everything from this. And we are performing a lot of analysis and optimization. And I'll go through them quickly because that's the point that is different from the other. Point to analysis. The last C here, where does it point to? Which memory does it share with other variable? Well, it depends. It could be with A, with B, or with nothing. If A or B are scalars, then you have a new fresh memory. So we have an analysis to tell you C can point to fresh memory, A or B. Another analysis, argument effects. Among all these functions, what are they doing with our arguments? Fibonacci is only reading n. Bar is calling a function that is only reading his argument. So bar is only reading L2. So there is interprocedural analysis inside. And foo is only calling a pure function too. So foo is only reading L plus updating some global state because we have a random call. From this, we can infer pure functions. F0 is pure because it only reads its argument and doesn't change the global state. F1 is not pure. It could be pure because F0 is pure, but it's changing the I/O. So F1 is not pure. And so the two above map, the first one could be performed in parallel because it's calling a pure function, and the second one is not parallel because it's not calling a pure function. So the purity of a function unlocks several optimizations. There's also a classical static compilation analysis, use def chains, which basically gives you the order of access to a variable. And in this small script, what is printed, it could be either A of the inside the if, but not the first A. So you can use it to perform some optimization too. So the first part in Pythran is to gather as many information as you can from your Pythran code. And that's not low-level information. That's high-level information that is only available in Pythran. And once you generate the C or C++ code, you will not get this information anymore. Thanks to this analysis, we can perform some optimization. For example, false polymorphism. Here, A seems to be a float, then a string, then a noun. But in fact, thanks to usedef analysis, you can say that you can rename the two A inside the if. And so that the first one is a float, and the second one is a nullable string. So this program is statically typed for Pythran. Here you have a bunch of map, ranges, some max. So all of these functions look like functional programming, but they are creating intermediate lists. There is an optimization in Pythran that turns the map into itertools.imap when it is legal. And it is legal in the first example because we iterate only once on the result. But in the second example, it's doubly illegal because we iterate twice on the result. So we can't get a generator instead, and we are updating the content. This unlocks some speedups. We also have constant folding, interprocedural constant folding. We can check that the sieve here is pure, and a pure function called on a literal can be substituted at compile time by the result. So there will be no code generated for this call in C++. You will only substitute by the result. So once you have your analysis, to turn them into code optimization. Then you want to optimize more, so you can, at the user level, add OpenMP annotation to your Python code. So using a string to do this, you can discuss about this, but still, that's the way I do it. You just say that the loop is parallel, and you describe the way each variable is accessed by each thread. So if you know OpenMP, this is trivial for you. If you don't, well, you just have to learn OpenMP. This code comes from the Python tutorial. I've just taken the pure Python version, added one or two annotation, turned it into parallel code through Pythran, and it runs twice as fast as the optimized code Kurt wrote in Python. So, and the gap between the two is very low, while to write good Python code, you have to learn much more things than you do for Python. Library level optimization, we are supporting part of Numpy. So Numpy is the key when you talk about scientific computing. If you come from static compilation and you look at Numpy, this smells like Fortran. In Python, there is Tran like Fortran. For the compiler guy I am, Fortran smells good, so Numpy smells good, and you can unlock a lot of parallelism from Numpy. You can aggregate point-to-point operation using expression template, which is a common technique from the C++ world, a bit of some kind of loop fusion for compiler guys. And we can also vectorize the resulting loop using SEC or AVX. So we're using NT2 as a backend to do this. And you can parallelize the underlying loop, only one loop because it has been fused, using OpenMP. So in the end, you get a parallel vectorized loop out of your high-level Numpy expression. So you gather as many information as possible, you turn them into code optimization, and you use a parallel runtime, a parallel library that can vectorize and parallelize your code. So that's how Pythran is working. Some benchmark, so this is a famous benchmark you can find on the internet. A very huge Numpy expression with a lot of scene, course. And if you run this into CPython, so that's still Numpy, but it doesn't run as fast as you could do. In Python, that's okay. You can also use numexp to JIT compile this expression into an optimized expression, which runs a bit faster than the original interpreter one. And you can run this through Pythran. If you enable vectorization on OpenMP, you get twice the performance you have with Python. And you don't modify the code. The learning step is very low. Another example, this is more naive code in the sense that it doesn't use Numpy accesses, but directly work on the array. So it's normal that the CPython version is really slow. So in Pythran, you can still work out some performance of this kind of code, and you can parallelize it as well. So even if you're not that good a programmer, Pythran can help you. So you don't educate people like this, but still it works. There is also this nqueen problem. So it is taken from the benchmark database of the now dead Unladen Swallow project. So this is real Pythonic code. So it's not only using arrays and for loops and ifs. There are generators, generator expression, list comprehension, sets. So that's high-level Python code, the kind of code Pythonists like to write. You can execute it, turn it into C++ code through Pythran, and it goes faster than Shetskin, because Shetskin is not doing any compile time optimization. It's just translating code from Python to C++. And it even goes faster than PyPy. Also, although PyPy has some dynamic transformation too. So there are, even for high-level code, we can reap some benefits through Pythran. So some engineering stuff. It's a GitHub project, BSD license, so nothing really surprising there. I have a personal Debian repository, so you can download the binary from there. It makes the installation easier, because you don't have this native library stuff to deal with. You can join us on Freenode, or just ask to the mailing list if you want to test the tool. It's really beta software. Okay, you don't want to, it will not work straight, but there is very small work to make it work for everybody. It's available on PyP. It's based on Python 2.7, 2.7. A lot of test case, more than 1 hour of validation on an 8-core machine. Some good coding rules. The backend is okay with both Clang and G++. So use the one you like as long as it's supporting C++ 11 well. So a few conclusions. Oh, great. Well, we will have time for questions. So the main page of the project is there. It's automatically generated, so not as sexy as you could think, but there is nothing to maintain there, so that's good for me. The idea I want to pass is that compiling Python is just more than translating it to a static language. There is more opportunities when you look at the Python language. There's a lot of things you can optimize, and you lose them if you go to C or C++. You have to do things before. That's the first point. The second point is that you still sometimes write loops. The French community is very good at optimizing loops through the polyhedral model, so that's what I'm working on in my postdoctoral position. So this may find its way to Python if there is an interest to this. And the last point is that I am looking for a job. So if you need an HPC guy, a compiler guy, or well, I'm open to any suggestion. And I am also open to questions.
Plenty of time for questions.
So the question is, why are you choosing C++ as a backend instead of LLVM? There are a lot of good properties when using source-to-source compilation. So the first answer would be look at my PhD. There is around 200 pages about the topic. The short answer is that as a compiler developer, it's really easier to develop when you can inspect C++ code instead of LLVM bytecode. In the end, you benefit from all the optimization G++ can do for you, and there are a lot of low-level optimization it can do for you. Another reason is that I am linking with several libraries that do a lot of stuff for me, and it would be more difficult to use this at the LLVM level. For example, the NT2 library, which is performing all the SEMD code, generic SEMD code generation, is a template-only library, so outside of C++, you can't use it. And when you write the runtime for Python, you're really nice. It's very nice to have a high-level language to write your runtime instead of a lower level. Let's go there. This one? There are a lot of difference in between Shetskin and Python. The good thing about Shetskin is that it supports a wider range of constructs from Python. For example, it supports user classes, but it trades this against very bad memory management. What Shetskin is doing is each time you need an object, you allocate it. And there is not a single delete in the code of Shetskin, in the code generated by Shetskin. Instead, there is a famous garbage collector for C++ that just stops the program every now and then, inspects the whole memory of the program, and checks if the address of the previously allocated data is still reachable somewhere in the memory. And if it is, then you just leave it. And if it's not, it deletes the memory. So memory allocation in Shetskin is very bad. So that's the first point. The second point is that Shetskin is not performing the iterator to generator transformation. And for this particular example, there are a lot of list comprehension. And so Shetskin keeps on allocating temporary lists, never freezing them. And instead, we are not allocating any lists. We are just generating C++ iterators. So everything is done in registers, not in memory. So we go really faster. Yeah? Oh,
When you're
sorry.
comparing,
Yeah?
SciPy, you've done any comparisons with Numpy?
I've not done any comparison with Numba, but generally when you go on Numpa blogs, what I have been doing, once they reach the Python performance level, yeah, it's okay. We are going beyond Python, so I'm pretty confident that for the code we can compile, we are doing better than Numba. And there are a few motivations for this. Numba is only relying on LLVM. So, to my knowledge, Numba does not perform many high-level transformation and delegates to LLVM all the transformation, which is nice, but you can't do some transformation at this level. You lose too many high-level information, so you can't use them. So that's the first point. And the second point is that LLVM vector instruction support is not as good as it could be. And NT2 we are using as a backend as vector support for all math functions from the C99 standard, and they are not available in the LLVM backend for x86. So some instruction can be vectorized through Pythran, and they can't be vectorized through LLVM, so Numba can't take advantage of them. The thing we are not doing is generating CUDA code or GPU code, and Numba is doing it, but on the non-operations version. So, yeah, there was a question like what he gave it. Yeah.
So there's really a lot of interest in compiling Python to something. It's many fun.
Yeah.
My understanding is there's not a lot of shared code in the project. Like the different communities haven't come up with a standard way of sharing work. Any comments on that? Or how could that be accomplished?
So the question is, there are many Python optimizers around there, and why aren't they sharing their code base? When I started this project, the first thing I wanted to do was to go to the Shedskin project and just add this optimization layer and take advantage of their type inference system that was already existing. And the code was not modular as it should be, so it was just not practical to do it. So that's the first point. You don't want to dive into the SciPy code base because it's really a different approach. That's not static compilation, so it takes it apart. And as I've been in compiler for a long time, Pythran is offering a path manager that makes it possible to turn Python code to optimized or transform Python code. So you can reuse several transformations from the Pythran project without using, for example, its backend. Or you can even use the whole path manager and in the end generate Python code, which will generally run slower because optimizations are good for C++ but not for Python. So there is, in this project, a code base that can be reused. We have planned to collaborate with the guy from MyPy, who presented his work at PyCon this year. And this is easy to integrate because he will work as a front end to give us type information, and then we can use them. So at a coarse grain, we can work. At finer grain, it's more difficult, but I had this in mind when designing the project.
Okay, let's thank the speaker one more time.